So yesterday we talked about open loop and closed loop systems and the characteristics associated with each of them, and we talked about the advantages and disadvantages associated with them, and we talked about certain examples of each of them. And today we'll discuss about the feedback systems and disturbances in the system. So we start with the disturbance. A disturbance is a signal that tends to affect the value of the output. And we gave example of disturbance in case of refrigerator. When we talked about refrigerator, we saw what are the disturbance there. Disturbance created inside the system are called internal disturbances, while external disturbances are generated outside the system. So again, for example, we talk about fridge. So in refrigerator, opening and closing of the door is a type of external disturbance. And in case of summer season, this is often little. So refrigerators are prone to more disturbances in summer season as compared to winter season. So depending on what situation the system is going to face, the disturbance varies, and it is random in nature. And again, internal disturbances are those disturbances that exist within the system. Example of which is changes in parameters of the system like resistor, inductor, and capacitor in electrical networks. And of course, in mechanical system, you have mass, spring, and damper systems. So these parameters, if they are going to change, will pose system an internal disturbance. So for example, if we talk about, we try to analyze system. Whenever we try to design any control system, so we first analyze it using some mathematical model. We try to formulate mathematical equations, and from that mathematical equation, we try to analyze how the system behaves at different situations. But what actually happens in real world is that these parameters associated with system like RLC and mass spring damper in mechanical systems, they change their value with time. So because of this change, the analysis that you do on paper comes out different from the analysis which actually exists, which actually in real time happens. An example of external disturbance is the wind gust on antenna during azimuth control. So we talked about antenna azimuth control in our first or second lecture, and we saw there that we didn't talk about any disturbance there. So we were considering only the ideal situation, that how the antenna azimuth is being controlled, how that angle is being controlled using potentiometers on both sides, on left side and right side. The voltage was being generated because of the difference in the position of the potentiometer, which was fed to a motor that controls the azimuth of the antenna. But we never talked about the disturbances which always exist, because there will always be wind that will be blowing and will be affecting the angle of the antenna, or the forces that is being exerted from the motor to the antenna for orienting it, and that disturbance will be also taken account when we will be analyzing such systems in real time. And of course, friction force acting on moving bodies are also external to the system, which always exist whenever you talk about motion of bodies. And now systems are broadly classified into two types. There are more classifications, but we'll limit ourselves to things that are a part of your course. So linear and non-linear systems. There are two types of systems. In fact, I tell you that linear systems are something that you always study on paper, on books. And whatever analysis you do, you consider the system to be linear. While in actual life and real time, you always have systems that are behaving non-linear, because systems are, we'll talk about this using some examples to explain, to make this clear later on. So linear systems are those systems which follow the principle of superposition and homogeneity. So what is principle of superposition? So the response, it is said that the response produced by simultaneous application of two or more different forcing functions, which is nothing but the input, is the sum of all the individual responses. What does it mean? That is, suppose that you're given a system which follows the principle of superposition, then if you apply an input x1 to it, this input x1 will be producing an output y1, And in the same system, if you're going to give an input x2, then we'll be producing an output y2. Then the system will be said to be following the principle of superposition if the system is provided with input x1 and x2, which is sum of the first input and second input. And if the system is going to produce output equal to sum of the first and second, that is y1 plus y2, then we say that the system is following the principle of superposition. And in case if you're not going to get y1 plus y2 in any case by application of x1 plus x2, then in that situation you will say that the system is not following the principle of superposition. Just summarize this. So I told you disturbance are the signals within the system that tends to affect the value of the output. So the output, that whatever you desire will be changed because of disturbance. And they are of two types. One is internal and external. Internal are faced because of the changes in the parameters like RLC and mass spring damper mechanical systems. While external disturbances are those which are coming from outside the system, for example, wind gust on the antenna azimuth during the azimuth control, and frictional forces acting on moving bodies. And then I told you about linear and non-linear systems. Linear systems are those which follow the principle of superposition and homogeneity. And superposition principle states that the response produced by simultaneous application of two or more different inputs is the sum of those inputs individual responses. So I gave an example that suppose you have a system which is fed with an input x1 and it produces output y1. So if the same system is fed by an input x2 in some other time which produces output y2, then this system is said to be following the superposition principle if on simultaneous application of the two inputs x1 and x2 produces output y, which is equal to the individuals inputs output y1 plus y2. So you gave x1 here, x2 here, producing y1 here, y2 here. This will be giving on applying input x1 plus x2 will be providing you output y1 plus y2. And superposition principle is said to be the necessary condition, because any system that does not follow superposition principle will not qualify as linear system. And the second principle that should be followed is homogeneity principle, which states that if any input x produces output y, and if you scale this input k times or a times, the output will also be scaled by the same value k or a. For example, if suppose you have a system and you provide input x to it which produces output y, and next time you scale the input by a quantity k, a constant k, so this will also be scaling the output by the same constant k. So if the system follows this principle, then it is said to be following homogeneity. And any system that follows the superposition as well as homogeneity is said to be linear. So for example, then in fact homogeneity principle can be derived from superposition principle. So in other words, if any system follows superposition principle, then it will always be following principle of homogeneity. So this is nothing but a subset of superposition principle. So this can be explained by the same example. If suppose I change this x1 to a value x, if x1 is equal to x and x2 is also equal to x, then in that case an application of x1 and x2 simultaneously will give you an input to the system equal to 2 times x. So and this x1 which is equal to x gives you an output y, and the second gives you an output y, because both inputs are same, then hence the output will also be same. And on simultaneous application of both the input will make the input 2 times x. So this 2x will produce an output 2y. So this is nothing but the principle of homogeneity, which says that if you scale the input by k, the output will also be scaled by k. So we are scaling the quantity by 2, and hence the output will also scale by the quantity. So we have an example of a spring. So suppose that the spring constant is k and it follows the following equation, f equal to kx. So we considered 3 different situations. So this equation is being followed considering that the spring is linear. And if you draw this particular equation graphically, you observe that f versus x will give you a straight line, which is nothing but the slope of this line is equal to k. So we assume that the spring equation for the spring that are assumed to be linear. So this is a linear graph. But in real life, in real time, what you have, the graph, it's not linear. It's not always linear. So this is because the spring has an elastic limit. So if you cross this elastic limit, it's going to behave non-linearly. So this is because beyond the elastic limit, you are going to deform these springs. So the shape of the spring will start changing if you go beyond the limits. So it may be possible that the spring to certain extension will follow the linear expression. But if you are going to expand it beyond the elastic limits, beyond that limit, or compress it beyond the elastic limits, then in that case the graph will not remain linear anymore. So it's going to become non-linear beyond its elastic limit. So this is something that you will always face in real world. But ideally, whenever you talk about paper works and you do analysis on paper, then you always take the graph to be linear, which actually does not happen in real time. The other classification of system is time variant and time invariant systems. So time variant systems are those systems in which the differential equations associated with the systems have coefficients a function of time. So again, we have an example. If suppose that for the same spring, if you have, instead of f equal to kx, you write f equal to kt. K is the spring constant, and if suppose that it becomes a function of time, somehow you design the spring in such a manner that it becomes a function of time. So I took this example just to explain you how the equations of a time variant system looks like. So if this coefficient is going to take a variable t associated with it, in that case the system will become time variant. So it means that the coefficient is also going to change with time. While if suppose that the system has a constant coefficient, where no coefficient associated with the system is a function of time, then in that case the system is time invariant. So all coefficients are not function of time. So if suppose that any system has multiple coefficients, for example, if you're going to write the equations for a mass spin damper system. I think my video is on. Let me turn off my video. So if the coefficient is a function of time, then in that case it qualifies as time variant system. For example, you talk about a space shuttle. So space shuttle has a mass ms, where ms is the mass of the shuttle without fuel, and mf is the mass of fuel. So both these masses, the mass of shuttle and fuel, together makes the total mass of space shuttle while it takes flight. And since mass of fuel is very much comparable to mass of shuttle, because it has to operate throughout the space, so a large amount of fuel is required. So during the flight, the mass of fuel, because the fuel keeps on burning, and thus the mass of fuel changes, and overall mass of the space shuttle will change with time. So this can be represented in terms of mathematical equation where the mass coefficient of this space shuttle will become a function of time. So such type of systems are called time variant system, because the coefficients of such system varies with time. Now if we talk about feedback is a process of measuring the output variable of the system to influence the same variable. So what you are going to do is you are going to pick the signal from the output through a feedback element. Feedback element is nothing but a sensor along with some processing unit, because in some cases the processing is required. In some cases you don't require any type of processing after sensors. For example, if you have input which is having the same unit as that of output, then in that case you are not going to process the sensed signal. But if suppose that output has a different form, like let's say you fed input in electrical form and the output came out in the form of temperature, then the temperature will be picked by temperature sensing device, and you'll be using a processing unit to convert that temperature into some electrical signal to be compared with input, because your input is electrical form. Otherwise, if suppose that input is also temperature and output is also temperature, in that case you're not going to process, because the sensor is going to pick this signal and will be converting in the form which will be comparable with input, not temperature, sorry. Input should not be temperature. Input should be some form which will be comparable with the sensor output. So this feedback element element allows the to pick the signal from the output or the actual output and compare with the reference or the desired output or the input. And after comparison, it will produce an error signal. So this error signal, if is finite, will command the controller to send signal to the plant, actuating signal to the plant. And then again, feedback are of two types. One is positive, the other is negative. So normally, one more thing, feedback is an operation that in the presence of disturbance tends to reduce the difference between the output of the system and the reference input or the desired output. So this is something that I explained yesterday. So you're going to pick the output, you're going to compare it with the input. If it matches, then error signal will be 0. If it doesn't match, the error signal will be finite, sending the signal to the controller to operate the plant accordingly. So the types of feedback, one is the positive feedback. Positive feedback is something that reinforces the behavior, while negative feedback corrects the behavior. Now what does this mean? So this can be explained through an example. Suppose that there is a football team and a coach who guides the player to play properly. So there are two ways that the coach can guide his players. Let's say a player kicked the football to the goal, but it couldn't gain any goal. So the goal was not in the right direction. So in such cases, there can be two ways or two behavior the coach can respond. One is that he can say the player who shot the ball, that was a good shot, you can do better, and next time he could do it properly. So such type of feedback would be qualified as positive. And on the other hand, if the coach is going to respond negatively, like he could say that the shot was very bad and you don't know how to play. So this type of feedback is qualified as negative feedback. Feedbacks used in control systems are always negative time. So there is some reason which will be explained later on. So this is negative. You can see the negative sign over here. So input is taken with a positive to comparator, while the signal that is picked from output through feedback element is fed with a negative sign. So this negative shows that the system is a negative feedback system. Had this signal been positive in place of negative, if you observe a positive signal over here, then the system is a positive feedback, which is actually not stable. So positive feedback systems are not stable, are never stable, unless you provide some sort of saturation limit to bring back the system back to 0 or back to some standard values or some reference values. So we are not going to talk about that because this is something that may exist in nature. But whenever we try to design system, we tend to make those systems have negative feedback. So this is how system will work, because your important signal is error signal. This error signal, if it's 0, will switch off the controller, but if it is finite, then in that case the controller is going to turn on. So that is why you always require the output signal to be negative in order to generate error signal. If you're going to take both of them positive, then the error signal will never be 0. So it will keep on coming finite, because input is always finite and output will keep on giving a positive signal, and they will add, and error will keep on increasing. So this way you cannot control any system. So you always require a negative feedback in order to control systems. So this will be more clear if we talk about analysis. If we do perform analysis of the system graphically later on. And the goals while you design a control system are: it should be stable. So whenever you incorporate feedback, I told you yesterday, open loop systems are always designed stable. But whenever you try to incorporate feedback, you provide feedback to open loop system in order to make it closed loop, then a problem that may arise is with the stability of the system. The system might become unstable when you employ a feedback to it. So this is an absolute requirement. You always want your system to be stable. You want certain output to be attained, the desired output to be attained. So this is only going to be possible if you have a stable system. So the first goal in designing any system is that the system is stable or not. And mind this, you have the part of stability, the chapter of stability, I think is third and fourth. So you'll be talking about stability in fourth unit. But whenever you design a system, your first target is to make it stable, and then you perform other sort of analysis later on. But in your syllabus, we talk about analysis first, then we switch to stability later on. The second part is tracking. So the system output must track the command reference signal as closely as possible. So after making the system stable, now when you start your analysis of the system, then you try to make the system response very close to the input that is given to it. So if suppose that I design refrigerator and the reference that I gave as input to the refrigerator is 0 degrees Celsius, then in that case I always like my refrigerator to attain 0 degrees Celsius. I don't want that it keeps on 5 degrees Celsius or goes below 0 to minus 5 degrees Celsius. So I want my system to achieve the output as accurate as possible. So this is known as tracking. The third is disturbance rejection. So I talked about disturbance in the previous slides. So the system output must be as insensitive as possible to disturbance input. So it means that you must design your system that any sort of disturbance that comes into the system should not make the output deviate from its desired values. So very small or slight deviations are allowed, but not much. So that was dependent on the tolerance band we defined. So in some cases, you want your variable to have very small tolerance band, very small limits beyond which it should not cross. In some cases, in some application, you can have broad tolerance band. For example, if you want to control the temperature of your room using AC, so you may set the temperature to 25, but in some cases you see that the system, because of some disturbance, like you don't have electricity for hours, then in that case you might get your room temperature to 30 or cross 30 degrees Celsius. So such type of disturbances should be rejected. So you may design your system to such type of disturbances. Robustness. The aforementioned goals must be met even if the model used in the design is not completely accurate or the dynamics of the physical system change over time. So these goals are supposed to be met if the system is not accurate, which means that if you're going to attain 25, you want to attain 25 degrees Celsius, but you couldn't somehow attain 25, but you are capable of attaining 27 degrees Celsius, or the dynamics of the physical system change over time. So you, for example, if you talk about electrical networks, you always observe in such networks that the dynamics may change because of fluctuations and because of changes in RLC. And if you look at the graphs of the power supply voltage and current in the grid, so you will see much disturbances in the form of fluctuations and in the form of deviations from 220 or 230 standard voltages and currents, and sometimes because of changes in the phases voltage. So these are something that the closed loop control system must take into account.